In this video, we are going to discuss about the effect of various capacitors on frequency response. So on the completion of this topic, the students will be able to determine the equivalent impedances that lie in parallel with the input and the output of the amplifier. So here the effect of the coupling capacitor. We know the reactance of the capacitor, which we call it as Xc, is equal to 1 divided by 2 pi into Fc. Here at medium as well as high frequencies, this factor F makes the Xc very small, so that all the coupling capacitor behaves as a short circuit. And also at the low frequency, this Xc increases. This increase in this Xc, that is reactance, drops the signal voltage across the capacitor, and then it reduces the circuit gain. Whenever there is an increase in the or decrease in the signal frequencies, the capacitor reactance increases, and also the gain continues to be fall, so that it reduces the output voltage. And here the effect of coupling capacitor is this one. And what is the effect of the bypass capacitors means, at low frequency this bypass capacitor is not short circuited, so this emitter which is not at the AC ground and also Xc which is parallel with this emitter resistance creates an impedance, and also the signal voltage which drops across this impedance, reducing the circuit gain. And the effect of the internal transistor capacitance, at high frequencies coupling and the bypass capacitors act as the short circuit, and also it does not affect the amplifier frequency response. At high frequencies, internal capacitance, commonly known as, we call it as jump capacitances. So here you can see the that is effect of this coupling capacitor in the case of the BJT as well as JFET. So in the case of BJT, you can see that is we are having three terminals. One is collector, base and emitter. So the capacitor which is placed in between the base and collector, we call it as base collector capacitance, and the capacitor which is placed between the base and the emitter, we call it as base emitter capacitance. And in the case of the JFET, we call it as, that is the capacitance which is present between the gate and the drain, we call it as gate drain capacitance, and the capacitance which is present between the gate and the source, we call it as gate source capacitance. And next one is the Miller's theorem. So in this transistor amplifiers, which is very necessary to split the capacitance between the input as well as output. So this can be achieved by using only through Miller's theorem. So in the following figure, you can find out the voltage gain, which represents the absolute voltage gain of the amplifier, that is at the mid-range frequencies, and also the C represents the capacitance, that is CBC in case of BJT and CGD in the case of FET. And this one is the splitting of capacitor using the Miller's theorem. So you can see the capacitors should be placed or splitted in the case of input as well as output. So in the case of input, if you are splitting out, you will be drawing as C of AV plus 1, and in the case of the output, you will be writing as C of AV plus 1 divided by AV. So this in this Miller's theorem only we can split the capacitor, and the needed of this one is we have to split the capacitor in the input side as well as output side. This can be done only through the Miller's theorem. So in Miller's theorem only we will be splitting out this input capacitances as well as output capacitances. So input can be split in the Miller's theorem in both the cases, that is in the BJT as well as MOSFET. There is FET devices also, we can use this one, as well as we can use it in the bipolar junction transistors also. Thank you.